For most of human history, we assumed the planets were the story. The large, visible, named objects, those were the things worth understanding. Everything else was just debris in orbit. Then we started looking at the moons. In 1979, a spacecraft passed close enough to one of Jupiter's moons to photograph its surface. What it showed stopped scientists cold. The moon was erupting, not with lava, but with plumes of material blasting hundreds of kilometers into space. It was the first time active volcanic eruptions had been confirmed on any world other than Earth, and nobody had predicted it. That was only the beginning. Another moon, smaller than our own, is hiding an ocean beneath its frozen surface that contains more water than every ocean on Earth combined. That ocean has never seen sunlight. It has been sealed in darkness for billions of years, and it may not be empty. One moon orbiting Uranus looks like it was shattered, split completely apart, and then pulled back together by gravity, leaving a surface so chaotic that scientists still argue about what could have caused it. A moon of Saturn has a thick atmosphere, producing complex organic molecules, the same chemical building blocks connected to life everywhere we have looked for it. And one moon orbiting Neptune travels in the wrong direction, backwards, against the flow of every other object in its system, a world that does not belong there, captured from somewhere else, its arrival violent enough to have permanently altered the structure of everything around it. Our solar system has more than 290 confirmed moons, and the more closely they are studied, the more the old assumption flips. The planets are not the most interesting part of this system. The moons are, and we have barely started. Today, we go through the strangest ones, what they are, what they contain, and what they suggest about the kind of solar system we are actually living in. If you enjoy content like this, subscribe and leave a like. It helps us more than you can imagine. Now settle in and let's talk about how one photograph changed everything. There was a long stretch of time when the sky seemed settled, a fixed arrangement that did not invite doubt. And for more than 1,600 years, after Aristotle described the heavens as perfect and unchanging, that stillness held its authority over every observation we made. Moons existed within that framework as minor companions, small, cold, and predictable, their purpose limited to orbit and reflection, never transformation. Then one winter night shifted the ground beneath that certainty. On January 7th, 1610, Galileo Galilei raised a simple telescope, magnifying objects by only 20 times, and turned it toward Jupiter. What you and I would have seen as faint points of light beside a bright disk became, through patience and repetition, something far more disruptive. Within days, those points moved, not randomly, but in clear paths around Jupiter itself. That motion carried a quiet consequence. If objects could orbit something other than Earth, then Earth was no longer central. The structure of the universe, once considered complete, opened. But even with that realization, moons remained conceptually small. For the next 367 years, we measured them, weighed them, and traced their paths with increasing precision. We treated them as finished objects, remnants of formation, rather than participants in ongoing processes. The reasoning felt solid. Small bodies cool quickly. Without internal heat, activity stops. Surfaces freeze into stillness. That assumption lingered, unchallenged, into the late 20th century. On March 5th, 1979, a spacecraft named Voyager 1 transmitted images from the outer solar system. Among them was a view of Io, one of Jupiter's moons. The image was not intended to reveal anything unexpected. It was routine navigation data used to refine position and trajectory. But when the frames were reviewed, a navigation engineer named Linda Morabito Notice something that did not belong. A faint, curved shape extended from the edge of the moon, like an umbrella caught mid-expansion. It was subtle, almost dismissible. For a moment, it nearly was. A flaw in the image seemed more likely than a change in understanding. But the shape persisted across frames. It was real. What Morabito had seen was a plume, material rising hundreds of kilometers above the surface. Not impact debris, not reflection, but an eruption, the first active volcano observed beyond Earth. Within 24 hours, another piece fell into place. A physicist named Stanton Peale had already submitted a paper describing a mechanism called tidal heating, a process where gravitational forces flex a moon's interior, generating heat through constant deformation. His work arrived almost simultaneously with the observation, no longer a prediction, not yet a confirmation. Together, they forced a revision. Moons were not static. They could generate energy, reshape themselves, and remain active across immense spans of time. Everything that follows grows from that convergence. A single image examined closely, and a theory arriving at precisely the wrong moment to be early and the right moment to change everything. If you were to stand above Jupiter's inner system and watch carefully, one moon would refuse to settle into stillness, its surface constantly rewriting itself faster than memory could keep pace. That world is Io, measuring 3,643 kilometers across, almost a twin in size to our own moon, yet behaving in ways that make familiar comparisons fall apart almost immediately. You would not see quiet plains. You would see motion everywhere. More than 400 active volcanoes mark its surface, each one a release point for energy that has nowhere else to go. No other place in the solar system concentrates this much activity into such a small body. Some of these features reach a scale that feels disproportionate. The volcanic region known as Pele holds a lava lake, roughly 200 kilometers wide, surrounded by a vast ring of red sulfur deposits that stain the landscape in tones visible from orbit. Another formation, Loki Patera, spreads across 21,500 square kilometers. Its molten surface does not remain still. It overturns in a slow, steady wave, cycling every 400 to 600 days with a rhythm that can be predicted years in advance. The temperatures reflect that intensity. Near active vents, heat climbs to 1,600 degrees Celsius, exceeding the hottest eruptions seen on Earth today. The chemistry differs as well. Sulfur dominates, shaping both color and behavior. But the source of all this energy does not come from within alone. It is imposed from outside, through a precise gravitational arrangement involving three neighboring moons. Io, Europa, and Ganymede are locked into what is called an orbital resonance, a repeating pattern where their orbits stay in strict ratios. For every 4 orbits completed by Ganymede, Europa completes 2, and Io completes 4. This pattern prevents stability. Io cannot settle into a perfect circle around Jupiter. Instead, its path stretches and tightens slightly with each orbit. As it moves closer and then farther away, Jupiter's gravity pulls unevenly on its interior, flexing it continuously. This process is known as tidal heating, meaning heat generated by repeated stretching and compression. The result is immense. The total energy released reaches around 100 trillion watts, comparable to every power station on Earth, operating together and then scaled far beyond that. That energy must escape. It does so violently. Io releases about 1 ton of sulfur and sulfur dioxide into space every second, feeding a vast cloud trapped within Jupiter's magnetic field. At the same time, its surface erases its own history. Impact craters cannot remain. New lava and deposits cover them within decades, leaving no long-term record behind. Recent observations confirm this pace. In February 2024, the Juno spacecraft passed within 1,500 kilometers, capturing images of fresh lava fields that had not existed during earlier missions. But if this level of activity can be sustained in rock alone, what happens when similar forces act on ice? Seen from far enough away, Europa offers almost nothing to hold on to. A pale sphere, faintly yellow, traced with thin reddish lines that seem too delicate to suggest anything happening beneath. It measures 3,121 kilometers across, slightly smaller than our moon, and at first glance, it appears unfinished, as if its surface has been smoothed over again and again until detail fades. But that absence of texture carries a different meaning. The surface is not old, it is being replaced. Beneath the ice lies a global ocean, hidden under a shell estimated between 15 and 25 kilometers thick. That ocean holds more liquid water than all of Earth's oceans combined, possibly 2 to 3 times as much, distributed in a continuous layer that wraps the entire moon. You are not looking at a frozen body, you are looking at a sealed one. The age of that ocean stretches back over 4 billion years. It has remained liquid longer than complex life has existed on Earth, longer than the continents have held their present shapes, longer than breathable oxygen has filled our atmosphere. Time here is not measured in changes we can easily observe. It is measured in persistence. The surface reflects this hidden motion. Impact craters are rare, almost absent, because the ice shell does not remain fixed. It is constantly being pulled apart and then refrozen, a slow cycle driven by the same tidal forces acting elsewhere, but expressed through ice instead of rock. The outer layer fractures, shifts, and reseals, leaving behind a record that is always incomplete. Those reddish lines crossing the surface have a name. They are called linea, long fractures filled with material that has risen from below. Minerals carried upward stain the ice, while radiation from Jupiter alters their chemistry, producing the colors we can see from orbit. Each line marks a place where the boundary between surface and ocean has thinned. Evidence for exchange does not end there. In 2013, observations from the Hubble Space Telescope revealed plumes of water vapor rising from Europa's southern hemisphere, reaching heights of around 200 kilometers before dispersing into space. These were not constant. They appeared, then disappeared, then returned again in 2016 at the same location. This repetition matters. It means the ocean is not fully sealed. Further analysis of the surface chemistry revealed sodium chloride, ordinary table salt, embedded within the ice. That detail connects the surface directly to the ocean below, indicating a saltwater composition that shares some similarities with Earth's own oceans, though under very different conditions. At the base of that ocean, pressure brings water into contact with rock. This creates what is known as a rock-water interface, a boundary where chemical reactions can release energy, similar to hydrothermal vents on Earth's seafloor. In those environments, entire ecosystems exist without sunlight, sustained only by chemistry. But the system here depends on a balance we do not fully see. The ice shell remains active, fractured, and mobile across immense spans of time. Something continues to supply the energy needed to maintain that state. And until we understand what sustains that motion, we cannot say whether the ocean beneath is simply chemical or something more. There are places on Europa where the surface stops behaving like a surface at all, where the continuity breaks and the ice seems to have lost its memory of how it was supposed to remain solid. These regions are called chaos terrain, a term that reflects what you see when order dissolves into fragments without a clear pattern to guide the eye. Across these zones, the ice appears disrupted, lifted, rotated, and set down again. Blocks of older crust sit at angles, separated by darker material that fills the gaps between them. Nothing aligns cleanly. The surrounding planes remain smooth, but here the geometry fractures into something unstable. One of the most studied examples is Connemara chaos. It spans roughly 50 by 100 kilometers, forming a landscape that resembles a frozen ocean after a violent disturbance. At high resolution, individual plates of ice appear to float within a matrix of refrozen material, as if they once moved freely before settling into place again. The arrangement is not random. When scientists examined the shapes of these blocks, they found that many could be matched to the spaces between them, like pieces of a puzzle that had been shifted apart and then partially returned. This indicates that the ice was once mobile, not entirely liquid, but softened enough to allow movement. The leading explanation involves warm ice rising from below, not melted into water, but softened to a state where it can flow slowly under pressure. This upwelling weakens the overlying shell, causing sections to detach, drift, and then refreeze as the heat dissipates. The process leaves behind a record of temporary instability, but this requires a condition that changes how we think about the shell itself. In these locations, the thickness must drop significantly, possibly to only a few kilometers. That reduction brings the underlying ocean much closer to the surface than elsewhere, narrowing the separation between two environments that are otherwise isolated. Because of this, chaos terrain becomes a focal point for exploration. If material from below has reached the surface recently, then these regions preserve the most accessible samples of the ocean's composition without requiring deep penetration. They are, in a practical sense, entry points. Another structure reinforces this idea. A feature known as Tyre spans about 38 kilometers and displays a series of concentric rings. It formed when an impacting object struck with enough energy to break through the ice shell and reach the liquid beneath. The resulting cavity collapsed and refroze, leaving behind a circular pattern that records the event. At a larger scale, the arrangement of fractures across Europa suggests that the entire ice shell is not fixed in place. It rotates slowly relative to the interior, a process called non-synchronous rotation, meaning the outer layer drifts independently over time. The shell behaves like a cracked layer, sliding over a deeper, mobile boundary. To understand this structure directly, a spacecraft launched in October 2024 now travels toward Europa. It carries radar designed to penetrate the ice, measuring thickness and identifying regions where the ocean approaches closest to the surface. Its path will focus on these fractured zones, where the separation between layers is already reduced. There is a point where size alone begins to change how we classify a world, and Ganymede sits directly on that boundary, large enough to challenge the categories we have grown comfortable using. At 5,268 kilometers in diameter, it exceeds the size of Mercury, and if you placed it in orbit around the Sun, you would call it a planet without hesitation. But it does not orbit the Sun. It circles Jupiter, carrying properties that do not match its classification. One of those properties lies hidden beneath its surface, yet extends far beyond it. Ganymede generates its own magnetic field, a magnetosphere, meaning a region of space controlled by the motion of charged particles within the Moon itself. This is not borrowed from its parent planet. It is produced internally through convection, the slow circulation of material driven by heat within a liquid iron core. That field shapes its surroundings. Near the poles, charged particles guided by magnetic lines collide with the upper atmosphere, producing auroral ovals. These were confirmed in 2015 using ultraviolet observations from the Hubble Space Telescope. You are looking at auroras on a moon, but their motion revealed something more subtle. As Jupiter's powerful magnetic field rotates, it exerts a shifting influence on Ganymede's own field, causing the auroras to rock back and forth. The movement was measurable, but it was smaller than expected. Something beneath the surface was absorbing part of that change. The explanation comes from electrical conductivity, the ability of a material to carry electric current. Salt water conducts electricity. Ice does not. By measuring how much the auroras shifted, scientists inferred the presence of a global saltwater ocean beneath the surface, acting as a conductive layer that dampens the external influence. That ocean is not shallow. Estimates place its depth at around 800 kilometers, extending far below the surface and enclosed between layers of high-pressure ice. These are forms of ice created under extreme pressure, denser and structurally different from the ice we know. The liquid layer sits between them, with the rocky interior at the base. Above this structure, the surface records a different history. Dark regions, heavily cratered, preserve an ancient landscape. Bright regions cut across them, marked by long grooves and ridges that stretch for hundreds of kilometers. These features suggest a period when internal forces reshaped the crust, then gradually diminished. We have not yet observed that interior directly, but that will change. A spacecraft launched in April 2023 is now on its way, designed to enter orbit around Ganymede in the year 2034. It will become the first mission to circle a moon other than our own, mapping its structure in detail. But the pattern already emerging raises a deeper inconsistency. Several of Jupiter's large moons contain oceans beneath their surfaces, sustained in different ways. Yet one of them, similar in size and composition, shows almost none of this activity. At the outer edge of Jupiter's major moons, there is a world that appears to have chosen stillness, holding its surface in a state that has barely changed for billions of years. This is Callisto, measuring 4,820 kilometers across, almost identical in size and composition to Ganymede, yet following a path that leads somewhere entirely different. When you look at Callisto, you do not see renewal. You see accumulation. Every square kilometer is layered with impact craters, each one overlapping another, forming a continuous record of collisions stretching back nearly 4 billion years. No process has erased them. No internal force has reshaped the crust. Time has been allowed to remain visible. The contrast with its neighbor is immediate. Where Ganymede shows signs of past restructuring, Callisto remains unchanged. There are no long grooves, no bright regions formed by resurfacing, no evidence of internal movement. It has not been reshaped since the early solar system settled into its present form. The reason lies in distance. Callisto orbits far enough from Jupiter to avoid the gravitational interactions that drive tidal heating in the inner moons. Without that constant flexing, its interior does not generate significant heat. It exists outside the system of forces that maintain activity elsewhere. In effect, it has been thermally isolated. But that isolation is not complete. During the 1990s, the Galileo spacecraft measured how Callisto responded to changes in Jupiter's magnetic field. The data showed a subtle but consistent pattern, one that could only be explained if a conducting layer existed beneath the surface. Conductivity here again points to salt water. This suggests a subsurface ocean. The presence of that ocean introduces a contradiction. Without tidal heating, there is no obvious energy source to keep water in a liquid state over geological time. One explanation considers radioactive decay within the rocky interior, a slow release of heat from unstable elements breaking down. It may provide just enough warmth to prevent complete freezing, but the margin is narrow. On the surface, the record of impacts reaches its most dramatic expression in a structure called Valhalla. It spans approximately 3,800 kilometers, forming a series of concentric rings that extend across much of the Moon. These rings mark the aftermath of a massive collision that melted the ice locally, sending waves outward before freezing into place. The environment surrounding Callisto adds another layer to its character. It orbits beyond the most intense regions of Jupiter's radiation belts, receiving far less energetic particle exposure than its inner counterparts. The radiation level is roughly 100 times lower than what is measured near Europa. This difference matters when considering presence. Studies of future exploration consistently identify Callisto as the most stable location for a human outpost within the Jupiter system. From here, operations could extend inward, allowing remote study of more hazardous environments without direct exposure. You would be standing on a surface that has not changed in billions of years, above an ocean that should not still exist, in a place defined as much by what it lacks as by what it contains. It begins with scale that feels almost dismissible, a moon only 504 kilometers across, small enough to fit within the borders of France with space remaining, orbiting quietly among Saturn's inner companions. Nothing in its size or position suggested importance. It should have been another frozen fragment, catalogued and left behind. But in 2005, as the Cassini spacecraft passed over its south pole, instruments recorded something that did not align with expectation. The data showed motion where none should exist. Scientists requested another pass, closer this time, narrowing the distance to confirm what had been glimpsed. What they found altered the context entirely. Along the southern region, a set of parallel fractures cut across the surface, each extending roughly 130 kilometers in length and about 2 kilometers in width. These features became known as the tiger stripes. From them, material was erupting continuously. The eruptions were not subtle. Jets of water vapor, ice particles, and gas were being expelled hundreds of kilometers above the surface, reaching heights near 200 kilometers before dispersing. Some of that material did not fall back. It escaped the moon's weak gravity and spread outward, feeding Saturn's E-ring with a steady supply of fresh particles. This meant the interior was active, but the composition of those plumes revealed far more. In 2008, Cassini flew directly through one of these jets at a speed of 64 kilometers per second. Its instruments captured the contents of the plume in real time. The sample included water, sodium chloride, carbon dioxide, methane, molecular hydrogen, and complex organic molecules containing chains of 10 carbon atoms or more. Each component added a piece to a larger structure. The silica nanoparticles were the first key indicator. These tiny particles form only under specific conditions, when water at temperatures above 90 degrees Celsius interacts with silicate rock. This implies that deep beneath the ice, liquid water is heated and circulated through a rocky interior. This process is known as hydrothermal activity, meaning water heated by internal energy flows through rock, exchanging chemicals and releasing energy. On Earth, this same process supports entire ecosystems in the deep ocean, independent of sunlight. The detection of molecular hydrogen reinforced this picture. Hydrogen is produced during a reaction called serpentinization, where hot water alters certain types of rock, releasing energy in the process. This energy becomes a fuel source for microorganisms that rely on chemistry rather than light. The organic molecules completed the set. These compounds represent the building blocks required for more complex structures, including membranes that define living cells. In a single pass through a plume, all three essential conditions associated with life were present: liquid water, chemical energy, and organic material. They were not hidden. They were being expelled into space, accessible without drilling or excavation. Yet the energy driving these eruptions remains difficult to account for. Surface temperatures near the fractures sit around -93 degrees Celsius, while the vents release heat measured at 15.8 gigawatts, exceeding what tidal forces alone are expected to provide. The imbalance remains. Before we ever looked outward for life beneath ice, we had already passed over a place on Earth that quietly held the same conditions, hidden in darkness, waiting without announcement. In February 1977, a small submersible named Alvin descended 2,500 meters into the Pacific toward a fracture zone known as the Galapagos Rift. The expectation was simple: cold rock, nothing more. But as the light swept across the seafloor, the terrain shifted from empty to structured. Columns of dark fluid rose from cracks in the crust, water heated far beyond the surrounding ocean, enriched with dissolved minerals pulled from the rock below. These features are called hydrothermal vents, meaning openings where heated water circulates through the crust and returns carrying chemical energy. Around those vents, life had organized itself in ways that did not depend on light. Tube worms grew to lengths of 2 meters, anchored in clusters. Clams opened in dense fields. Crabs and shrimp moved through the flow. Fish passed through a space that should not have supported them. The ecosystem was complete. The source of its energy was not sunlight, it was chemistry. At the base of this system were bacteria known as chemolithotrophs, organisms that extract energy from chemical reactions involving inorganic compounds. They use substances like hydrogen sulfide, methane, and molecular hydrogen, all produced when hot water reacts with rock in a process called serpentinization. This reaction alters the minerals and releases energy that life can use directly. This means the food chain begins without light. It builds upward from chemical gradients alone. Since that first descent, similar ecosystems have been found across multiple ocean basins, each one independent, each one sustained by the same underlying process. The pattern is consistent. Where heat, water, and rock meet, chemistry can support life. The range of conditions extends further than expected. Microorganisms classified as extremophiles have been observed surviving at temperatures above 120 degrees Celsius in environments where acidity ranges from 0 to 12.5 on the pH scale and under pressures exceeding 1,000 atmospheres. These values describe conditions that were once considered uninhabitable, but they are occupied. The significance of that discovery changes when you place it beside what we have already measured elsewhere. The same chemical compounds identified in these environments on Earth have been detected in material originating far beyond it. Hydrogen, methane, salts, and organic molecules appear together under conditions that mirror those deep ocean systems. If the first hydrothermal ecosystem had been discovered on another world before we found it here, it would have been described as decisive evidence. Instead, it was beneath us all along, unnoticed until technology reached it. But once that context is established, a different standard emerges. If life does not require sunlight, and if chemical energy alone can sustain complex systems, then the absence of light cannot be used as a reason to exclude the possibility of life elsewhere. So, when material rises from a distant ocean carrying the same ingredients, what remains as the basis for assuming that nothing is there? If you were to descend through Titan's atmosphere, you would lose sight of everything familiar long before reaching the surface. The sky, closing in around you as layers of dense haze, scatter and absorb light until direction itself becomes uncertain. This is Saturn's largest moon, measuring 5,149 kilometers across, larger than Mercury, yet wrapped in an atmosphere thick enough to conceal its own landscape. The descent would not be brief. When a probe entered this atmosphere in January 2005, it required 2 hours and 27 minutes to fall from the upper layers to the ground. That duration reflects density, a continuous resistance that slows motion and diffuses visibility. Even at the surface, you would not see Saturn above you. The pressure here reaches about 1.5 times that of Earth at sea level. You would feel weight, but not enough to harm you directly. The barrier is elsewhere. Temperatures settle near minus 179 degrees Celsius, and oxygen is absent. Survival depends on heat and air, not structural protection. But within these conditions, a system operates that mirrors something much more familiar. Titan possesses a methane cycle, functioning in the same way as Earth's water cycle, but replacing water with methane at every stage. Methane evaporates from liquid reservoirs, rises into the atmosphere, condenses into clouds, and returns as rain. That rain does not vanish, it flows. Channels cut across the surface, forming rivers that carry liquid methane toward low regions near the poles. There, the fluid collects into lakes and seas. The largest of these, Kraken Mare, spans around 400,000 square kilometers and reaches depths of at least 300 meters, with some estimates suggesting greater depths based on radar data. These bodies of liquid remain stable. They do not evaporate instantly or freeze solid. The balance of temperature and pressure allows methane to persist as a liquid, making Titan the only place beyond Earth where standing liquid exists on a surface. Time here follows a different rhythm. Saturn takes about 29.5 Earth years to complete one orbit around the Sun, which means Titan experiences seasons that last roughly 7.5 Earth years each. Over that cycle, cloud systems shift, rainfall patterns change, and the distribution of surface liquid evolves. Observations from orbit have tracked this movement directly. Methane clouds migrate from one hemisphere to the other, responding to changes in solar heating, producing a global weather system that operates continuously across decades. Even sound exists here, faint but present. When the descending probe reached the surface, it carried a microphone. It recorded the movement of wind and the contact between its landing structure and the ground. A subtle crunch over a surface composed of frozen hydrocarbons and water ice. But beneath this familiar structure, everything remains inverted. The liquids are hydrocarbons. The ice behaves as rock. The sky filters light into a constant orange haze. And within that environment, chemistry proceeds along pathways that do not require warmth, only time and the steady cycling of material. Long before anything reaches the ground, Titan's atmosphere is already assembling complex chemistry, building structures high above the surface where sunlight and energetic particles slowly reshape simple molecules into something more intricate. You would not see this happening directly. The haze obscures it. But within that haze, reactions continue without interruption. The material forming that orange sky is known as tholins, a term introduced in 1979 by Carl Sagan to describe complex organic substances that resemble the early chemical mixtures thought to precede life. These compounds are not imported. They are created in place. In the upper atmosphere, nitrogen and methane molecules are broken apart by ultraviolet radiation and high-energy particles. Their fragments recombine into longer chains, forming nitriles, amino acid precursors, and polycyclic aromatic hydrocarbons. These are molecules that appear in studies of early Earth chemistry, components that can lead toward more structured biological systems under the right conditions. Once formed, these compounds do not remain suspended indefinitely. They drift downward, settling through the atmosphere as fine particles. Over time, they accumulate on the surface in layers that can reach meters in thickness, creating vast deposits of organic material across Titan's landscape. This process has been replicated on a smaller scale. In the same year the term was introduced, Sagan and his colleague Bishan Kare exposed mixtures of nitrogen and methane to controlled radiation in a laboratory. The resulting material matched the spectral properties observed on Titan, confirming that the same chemistry could occur naturally under those conditions. The scale, however, is what changes the significance. Estimates suggest that Titan's surface holds organic carbon in quantities hundreds of times greater than all known fossil fuel reserves on Earth. But here, it is not concentrated in isolated deposits. It is distributed globally, forming a continuous chemical record. At low temperatures, additional behaviors emerge. Laboratory experiments have shown that some of these organic compounds can organize themselves into vesicles, small enclosed structures with boundary layers that separate an interior from the surrounding environment. These formations resemble early membrane structures, similar in concept to the lipid vesicles associated with the first cellular systems on Earth. The environment remains different. The solvent is methane, not water. The temperature is far lower, but the principle of self-organization appears to persist. There is also a subtle imbalance that remains unresolved. Measurements near the surface show that hydrogen levels are lower than expected based on known atmospheric reactions. Something may be consuming it. The process has not been identified, but if chemical systems can build complexity in an environment this cold, using materials that fall continuously from the sky, then the boundary between inert chemistry and organized structure becomes less defined than it once appeared. Across Titan's equator, the surface arranges itself into long, parallel bands that stretch beyond the horizon, repeating with a consistency that suggests a steady force shaping them over immense distances. These are dune fields, extending for hundreds of kilometers, aligned in rows that run east to west across the landscape. At first glance, they resemble deserts on Earth, but the material forming them is entirely different. Instead of silicate sand, the grains are composed of organic particles, likely derived from the atmospheric chemistry above. These particles begin as fine residues, then dry as methane evaporates, gradually compacting into grains comparable in size to coarse sand. Over time, wind gathers and organizes them into ridges. The scale is difficult to match. Individual dunes rise to heights of about 100 meters and can extend for up to 1,500 kilometers in length. They rank among the largest active dune systems known anywhere in the solar system. But their orientation presents a contradiction. The ridges point from west to east, indicating that material has been pushed in that direction over long periods. Yet measurements of Titan's surface winds show that most of the time, air moves from east to west at low altitudes. The dunes appear to be shaped by winds that do not dominate the present conditions. This inconsistency required a different explanation. When scientists modeled Titan's seasonal cycles, a pattern emerged that resolves the mismatch. During Saturn's equinox, which occurs once every 15 Earth years, the atmospheric circulation shifts briefly. For a short period, strong eastward winds develop, capable of moving large quantities of material. These events are rare and transient. They do not last long, but their strength exceeds that of the prevailing winds during the rest of the cycle. Even though east to west winds dominate most of the time, they are not powerful enough to significantly rearrange the dunes. The less frequent eastward gusts carry more influence. As a result, the dune fields record the effects of storms that occur only once every 15 years. The landscape is shaped not by constant forces, but by infrequent events that leave lasting marks. Beneath these dunes, another layer of information remains partially hidden. Radar observations have revealed patterns that resemble ancient river channels, now inactive. Their paths do not align with the current methane drainage system, suggesting that Titan's climate has shifted over time, alternating between periods with different distributions of liquid. This implies that the surface we see is not fixed. It evolves as the balance between atmosphere and liquid reservoirs changes. A mission scheduled to arrive in the mid-2030s will explore this directly. A rotorcraft designed to move between locations will sample both the dune material and the solid ice beneath it, analyzing how far the organic chemistry has progressed. But even before those measurements are made, the structure of the dunes reveals something fundamental. On Titan, change does not require constant motion. It can emerge from rare events, spaced across years, each one leaving an imprint that persists long after the wind has passed. For a brief moment in January 1986, a spacecraft passed a small moon of Uranus and returned images that would remain the only close record of its surface for decades. That moon is Miranda, only 472 kilometers across, the innermost of Uranus's major companions, and everything we know comes from that short encounter. What the images showed did not fit a single history. Instead of a continuous surface, Miranda appears divided into regions that do not blend. Ancient cratered plains sit directly beside younger terrain, marked by ridges and grooves, with no gradual transition between them. The boundaries are abrupt. Entire geological eras seem placed side by side, as if assembled rather than formed in sequence. The arrangement suggests disruption, but not in a simple way. Early interpretations propose that Miranda had been shattered by a massive impact and later reassembled by gravity, its pieces settling into a new configuration. But when scientists examined the geometry more closely, the likelihood of such a process producing these specific patterns proved extremely low. A different explanation emerged, one that involves internal heating applied unevenly. Miranda may have once been locked in an orbital resonance with another moon, Umbriel. In this context, resonance means a repeating gravitational interaction that can generate heat through internal flexing, but unlike the sustained interactions seen elsewhere, this one may have been temporary. While active, it would have concentrated energy into specific regions of Miranda's interior, warming some areas while leaving others largely unchanged. The heated zones would have softened, fractured, and resurfaced, creating the younger terrains we observe. Once the resonance ended, the process stopped, leaving a patchwork frozen in place. Among these features, one stands apart in scale. Verona Rupes rises between 15 and 20 kilometers above the surrounding terrain, making it the tallest known cliff in the solar system. For comparison, the highest sea cliff on Earth, located on Baffin Island, reaches about 1,250 meters. The difference is not incremental. It is an order of magnitude. The effect of this height becomes clearer when combined with Miranda's gravity. Surface gravity here is roughly 0.8% of Earth's. If you were to release an object from the top of Verona Rupes, it would fall slowly, taking around 12 minutes to reach the base. When it arrives, its speed would approach 100 kilometers per hour, the result of constant acceleration over an extended duration. The landscape around this cliff reflects the same fragmented history. Large blocks appear tilted, intersected by deep valleys and abrupt ridges. Nothing suggests a gradual evolution. Instead, it records episodes that began and ended under different internal conditions. And yet, all of this understanding is based on a narrow window of observation. Voyager 2 spent only about 6 hours in close proximity to Miranda, capturing a limited set of images before continuing its path outward. No mission has returned since. You are looking at a world defined by incomplete information, where the available evidence points to processes that no longer operate, preserved in a configuration that remains only partially explained. There is a direction most moons follow without exception, a shared motion inherited from the disk of material that formed alongside their planets, moving in the same sense as rotation, aligned with the system that created them. But Triton does not follow that direction. It moves against it. Triton orbits Neptune at an inclination of about 157 degrees, traveling in the opposite direction to the planet's rotation. This is called a retrograde orbit, meaning motion reversed relative to the primary body. For large moons, this configuration cannot arise from local formation. The mechanics do not allow it. So Triton did not originate here. The most consistent explanation is capture. Triton began as an independent object in the outer solar system, likely within the Kuiper Belt, a distant region populated by icy bodies left over from planetary formation. At some point, billions of years ago, it passed close enough to Neptune to be drawn in, its path altered permanently by gravity. But capture at this scale is not a quiet process. A body measuring 2,707 kilometers across carries enough mass to disrupt whatever system it enters. Any pre-existing moons would have experienced severe gravitational disturbances. Some would have been ejected into space. Others may have collided, breaking apart or merging under chaotic conditions. Triton itself would not have settled immediately. Its initial orbit would have been highly elongated, moving far from Neptune and then returning close again in repeated cycles. Over time, tidal friction, the gradual conversion of orbital energy into heat through internal deformation, would have reduced that eccentric path into a more circular one. That energy had to go somewhere. It was absorbed by Triton's interior, generating enough heat to melt large portions of it. In effect, the moon's earlier history was erased, replaced by a new geological starting point shaped by that intense phase of internal change. Today, Triton remains active in ways that contrast with its environment. Neptune orbits at a distance roughly 30 times greater than Earth's distance from the Sun, and surface temperatures on Triton drop to about -235 degrees Celsius, approaching the lowest temperatures physically achievable. Yet activity persists. In 1989, a spacecraft observed dark plumes rising from Triton's south polar region, nitrogen gas erupting from beneath the surface and spreading across the terrain in streaks. These geysers are driven not by internal heat alone, but by seasonal warming of surface layers, where sunlight penetrates translucent ice and triggers sublimation, the direct transition from solid to gas. The orbit that brought Triton here continues to shape its future. Because it moves in the opposite direction, Tidal interactions with Neptune do not stabilize its motion, they remove energy. Gradually, Triton is spiraling inward. This process unfolds over immense spans of time. In approximately 3.6 billion years, Triton will cross a boundary known as the Roche limit, the distance at which tidal forces exceed the strength of the body itself. When that threshold is reached, the moon will not remain intact. It will be pulled apart. There are worlds that reveal their structure immediately, and there are others that conceal it so completely that even repeated observation finds nothing to hold on to. Mimas belongs to the second group, a small moon, only 396 kilometers across, dominated by a single feature, so large it defines its appearance. That feature is Herschel crater. It spans nearly 1/3 of the moon's diameter, a vast depression with a central peak rising from its floor. From a distance, it gives Mimas a familiar outline, but beyond that visual impression, the surface offers little variation. For a long time, that simplicity shaped its reputation. Mimas was considered inactive, lacking any signs of internal motion, no fractures, no plumes, no regions suggesting recent change. It sat at a distance from Saturn, where tidal forces were weaker, and by every expectation, it should have cooled completely. But the absence of visible activity does not guarantee an absence of structure beneath. In 2024, researchers revisited data collected decades earlier, focusing on subtle variations in Mimas's rotation. As it orbits Saturn, the moon does not spin perfectly uniformly. It exhibits a small oscillation known as libration, a slight wobble that can be measured precisely over time. Libration reflects internal distribution of mass. If the interior is uneven, the rotation responds. The observed wobble could not be explained by surface shape alone. Scientists tested different internal models, adjusting the configuration of rock and ice, searching for a structure that would reproduce the motion. Two possibilities remained. One involved an elongated core. The other required a global layer of liquid beneath the surface. Further analysis favored the second option. The data align most closely with a subsurface ocean beginning roughly 20 to 30 kilometers below the surface and extending through much of the interior. This implies that beneath an unbroken outer shell, liquid water is present, moving independently of the solid crust above it. The age of this ocean adds another layer. Based on models of heat generation and ice melting, it appears to have formed between 5 and 25 million years ago. In geological terms, this is recent, younger than many mountain systems on Earth, younger than some forms of life. This makes Mimas one of the youngest ocean worlds known, yet the surface remains unchanged. There are no visible fractures or eruptions indicating activity below. The ice shell is still thick, still intact, preventing heat from reaching the exterior. The ocean exists, but it has not yet altered the surface in ways we can detect. This creates a different kind of uncertainty. If an ocean can exist here without leaving any clear external signature, then the absence of surface evidence cannot be used as confirmation of absence below. The distinction between active and inactive becomes less reliable when interior conditions are hidden behind stable exteriors. What appears simple may not be simple at all. There are objects that spin with quiet regularity, presenting the same face each time they complete an orbit. And then there is Hyperion, a body that never settles into a predictable orientation, shifting its position in a way that resists long-term calculation. If you were to track it across successive orbits, you would find no repeating pattern. Hyperion is one of Saturn's outer moons, measuring roughly 360 by 266 by 205 kilometers. Its shape is irregular, not rounded by gravity, but left uneven, as if it had been interrupted before it could settle into equilibrium. This form reflects its origin. At some point in the past, a larger body broke apart through a collision, leaving fragments that did not recombine into a single sphere. Hyperion is one of those remnants, a structure defined more by absence than by cohesion. It is the largest known moon that has not become spherical under its own gravity. But its shape is only part of its instability. Most moons rotate in a consistent manner, their spin synchronized, or at least regular. Hyperion does not. Its rotation is chaotic, meaning small differences in initial conditions lead to large changes over time, making its orientation impossible to predict beyond a limited window. This behavior was described in theoretical models before it was observed directly, and Hyperion provided one of the first confirmations that such motion occurs naturally. As it moves through space, its axis shifts unpredictably. One orbit does not resemble the next. The surface reflects this irregularity. Instead of smooth craters, Hyperion is covered in deep, sharply defined pits, giving it an appearance similar to a sponge. These features are not the result of typical impact excavation. They form because of the moon's internal structure. Hyperion has an unusually low density, approximately half that of water ice. This implies that a significant portion of its volume, possibly up to 40%, consists of empty space. It is not a solid body in the usual sense. It is a loosely bound collection of material, with gaps between its components. When an impact occurs, the energy does not carve out a clean, rounded crater. Instead, it compresses the porous structure, creating steep-sided depressions with sharp edges. The material absorbs the force rather than ejecting it outward. Within these pits, darker substances accumulate. Organic material, similar in composition to compounds found elsewhere in the Saturn system, settles into the low areas. Because Hyperion's gravity is weak, it cannot easily redistribute this material once it arrives. The darker regions remain in place, gradually coating the interior of the pits. The combined effect is a surface that records both structure and motion, irregular in form and unpredictable in orientation. If you were to observe Hyperion at two different times, separated by weeks, you could not confidently determine how it had rotated between those observations. Its path through space is known, but its facing direction is not. But this unpredictability is not random in the sense of lacking cause. It arises from precise conditions, where shape, mass distribution, and external influences combine to produce motion that cannot be simplified into a repeating cycle. Some worlds reveal their nature by what they hide, appearing and disappearing in a pattern that suggests something is changing, when, in fact, the change is simply which side you are allowed to see. In 1771, Giovanni Cassini observed a moon of Saturn that behaved in exactly this way. It would appear on one side of the planet, then vanish when it moved to the other. The object had not moved out of sight. It had faded. Cassini realized that the disappearance could not be explained by orbit alone. The only consistent explanation was that the moon itself was uneven in brightness, one side reflecting light strongly, the other absorbing it almost completely. When the darker hemisphere faced Earth, the moon became nearly invisible through his telescope. That deduction held, but the cause remained unresolved for centuries. Iapetus presents one of the most extreme contrasts known. One hemisphere reflects light like fresh snow, while the opposite side is coated in material so dark it reflects only a few percent of incoming sunlight. The boundary between them is sharp, dividing the surface into two distinct domains. The explanation required time to assemble. It begins far from Iapetus itself, with small outer moons shedding dark material into space. One of these, Phoebe, contributes a continuous stream of fine particles that drift inward under the influence of Saturn's gravity. As Iapetus orbits, one hemisphere leads in its direction of motion. That leading side encounters the incoming dust, collecting it gradually. Over long periods, a thin layer forms, darkening the surface, but this alone cannot produce the observed contrast. A second process amplifies the difference. Dark material absorbs more sunlight, raising local temperatures slightly compared to the surrounding ice. This causes water ice to sublimate, transitioning directly from solid to vapor and migrate across the surface. When that vapor reaches colder regions, it condenses again, depositing fresh ice. This process is known as thermal segregation, meaning heat drives the separation and redistribution of materials. It reinforces itself. The dark side grows darker as ice is lost, while the bright side grows brighter as ice accumulates. Over time, the contrast becomes extreme. Iapetus also carries a structure that remains difficult to explain. A ridge runs along its equator for about 1,300 kilometers, rising up to 20 kilometers in height. It follows the equator with unusual precision, forming a continuous line that divides the surface. No other object shows a similar feature. Several ideas have been proposed, including the remnants of a collapsed ring system, compression from a faster past rotation, or the result of an early collision that shaped the moon's structure. None have been confirmed. None. The rotation of Iapetus adds to its character. It is tidally locked, meaning it rotates once for every orbit around Saturn. One rotation takes 79 Earth days, so each day on Iapetus lasts longer than 2.5 months. As it turns, the same pattern repeats, one side bright, the other dark, a contrast that took over 3 centuries to explain and still carries features that resist a single, complete answer. Far beyond the familiar arrangement of Saturn's larger moons, there is an object moving along a path that does not align with the system around it, tracing an orbit that immediately suggests a different origin. This is Phoebe, circling Saturn at a distance of about 12.9 million kilometers, far outside the region where regular moons formed. Its motion confirms that difference. Phoebe travels in a retrograde orbit, meaning it moves opposite to Saturn's rotation, and at an inclination that places it well outside the plane of the main system. These characteristics indicate that it was not created alongside Saturn. It arrived later. When a spacecraft passed Phoebe in June 2004, it provided the only close view we have. The surface appeared dark and heavily cratered, marked by impacts that had accumulated over long periods. In several locations, those impacts had exposed brighter material beneath, revealing streaks of ice where the outer layer had been disrupted. Analysis of the surface composition provided a clearer origin. The materials present, water ice, carbon dioxide ice, organic compounds, and silicates, match those found in objects from the Kuiper Belt. This region, located beyond Neptune, contains remnants from the early solar system that have remained largely unchanged. Phoebe is one of those remnants. It was captured by Saturn at some point in the distant past, drawn into orbit, and preserved in a new environment. But that preservation is not complete. Phoebe continues to interact with its surroundings through a slow process of erosion. Micrometeorites, small particles moving at high speed, strike its surface continuously. Each impact releases fine dust, lifting material into space. Over time, this material forms a diffuse structure surrounding Saturn, known as the Phoebe ring. The scale of this ring extends far beyond what we can see directly. It stretches from about 128 to 207 times the radius of Saturn, forming one of the largest structures in the solar system. Despite its size, it remains nearly invisible, detectable only in infrared observations because of its low density. The dust within this ring does not remain static. It gradually moves inward, influenced by gravitational forces and radiation effects. As it drifts, it encounters other moons, including one whose surface records this interaction. The dark material coating the leading hemisphere of Iapetus originates from this process. Particles shed from Phoebe travel inward and accumulate over time, altering the appearance of another world across a vast distance. But Phoebe's significance extends beyond its role in shaping nearby bodies. Because it formed in the outer solar system and remained largely unchanged before capture, its composition preserves conditions from the early solar nebula, the cloud of gas and dust from which the planets formed. In this sense, Phoebe functions as a record. It holds chemical information from the first stages of the solar system, a snapshot of materials that existed before planets and moons settled into their current configurations. You are not just observing a captured moon. You are looking at material that has remained in cold storage for billions of years, carrying information from a time when the system itself was still taking shape. If you could watch Saturn's rings over the course of weeks, not moments, you would begin to notice that one narrow band refuses to remain still, its structure shifting in ways that suggest constant interference rather than quiet orbit. This is the F ring, a thin, braided strand just beyond the main system, shaped by forces that operate on timescales short enough to observe directly. The changes are not random, they are guided. Two small moons orbit on either side of this ring, moving along paths that keep them close enough to influence its structure. These are known as shepherd moons, bodies that maintain and sculpt ring material through their gravitational pull. In this case, the inner moon is Prometheus, an irregular object measuring about 136 kilometers across at its longest dimension. Prometheus moves slightly faster than the ring itself. Its orbit is shorter, which means it overtakes the same region of the ring roughly every 19 hours. Each time it approaches, its gravity draws a portion of the ring's particles toward it, stretching the material into a narrow streamer. As it continues along its path, the connection breaks, and the particles fall back into the ring. This repeated interaction carves visible patterns. Dark channels appear where material has been pulled aside, then gradually refill as particles redistribute. The process repeats with each pass, creating a cycle that can be tracked over time. These patterns are consistent enough that they have been used to refine measurements of Prometheus's orbit with high precision. But Prometheus does not act alone. On the outer side of the ring, Pandora follows a slightly different path. Its gravitational influence pushes particles inward, counteracting the outward pull from Prometheus. Together, these two bodies confine the F ring within a narrow region, maintaining its structure through opposing forces. The ring itself responds continuously. Clumps of material form, disperse, and reform. Spiral features emerge and unwind. Bright knots appear after collisions with smaller objects, then fade as the shepherd moons redistribute the debris. These changes occur over weeks and months, making the F ring one of the most active structures we can observe in real time. The interaction between the moons is not simple either. Prometheus and Pandora influence each other gravitationally, altering their orbits in subtle ways that accumulate over decades. Their paths shift, not in a fixed pattern, but through a complex exchange of energy that resists long-term prediction. This system provides more than a dynamic view. It offers a model. By observing how small bodies maintain and shape a ring, we gain insight into processes that operated much earlier, when planetary systems were still forming. The same principles that guide these interactions would have influenced the distribution of material in the early solar system, shaping the structures that later became planets and moons. Here, those processes remain visible, not as distant history, but as ongoing motion, a system where gravity acts continuously to organize matter into patterns that are never entirely fixed. If you stood on the surface of Mars and watched its inner moon cross the sky, you would notice something immediately unusual. It rises in the west and sets in the east, reversing the motion we expect from a natural satellite. This is Phobos, the closer of Mars's two moons, and its behavior reflects how tightly it is bound to the planet beneath it. Phobos measures only about 27 kilometers across at its widest point, an irregular body covered in a layer of loose material called regolith, meaning fine dust and fragmented rock that has accumulated over time. In some regions, this layer reaches depths of up to 100 meters, soft enough to shift under minimal disturbance. Its orbit lies just 6,000 kilometers above Mars's surface, closer than any other known moon orbits its planet. At that distance, it completes 3 full revolutions in a single Martian day, moving faster around Mars than the planet rotates beneath it. This difference creates the reversed motion observed from the ground. But this proximity comes with a consequence that unfolds slowly. Mars exerts a tidal force on Phobos, a difference in gravitational pull across the moon's body that stretches it slightly with each orbit. Over time, this interaction removes energy from Phobos's motion, causing its orbit to shrink. The rate of inward movement is small, about 1.8 centimeters per year, but it is continuous. Given enough time, the effect accumulates. In approximately 50 million years, Phobos will cross a boundary known as the Roche limit, the distance at which tidal forces become stronger than the moon's own gravity, holding it together. When that point is reached, the structure of Phobos will no longer remain intact. It will break apart. The resulting debris will not fall directly onto Mars. Instead, it will spread into a ring system, forming a temporary structure that may persist for millions of years before dispersing or eventually descending toward the planet. Mars, which currently has no rings, will briefly acquire one formed from the remains of its own moon. Evidence that this process has already begun appears on the surface. The largest feature on Phobos is Stickney Crater, a depression 9 kilometers across, nearly half the moon's diameter. The impact that created it was large enough that it could have shattered the entire body. Instead, Phobos remained intact, but the event left structural weaknesses. From the region around Stickney, sets of parallel grooves extend across the surface. These were once attributed directly to the impact, but further analysis suggests another cause. The grooves align with patterns expected from tidal stress, fractures forming as Mars's gravity continues to pull unevenly on the moon. These cracks indicate that Phobos is not a rigid body. It is already responding to the forces that will eventually dismantle it. A future mission plans to examine this process more closely. In the early 2030s, a spacecraft will land on Phobos, collect material, and return it to Earth for study, providing direct insight into its composition and internal structure. For now, The motion continues, each orbit bringing Phobos slightly closer, its path narrowing over time, a trajectory that leads not to stability, but to gradual disassembly. There are systems in the solar system that we have only seen once, briefly, as if through a passing glance, and everything we think we know about them still rests on that moment. Uranus and its moons belong to that category, observed in detail only during a narrow interval in January 1986, when a single spacecraft moved through and continued outward. Uranus has 28 confirmed moons, each named after characters drawn from the works of William Shakespeare and Alexander Pope, a naming tradition unique among planetary systems. Among them, 5 stand apart in scale: Miranda, Ariel, Umbriel, Titania, and Oberon, ranging from just under 500 kilometers to over 1,500 kilometers in diameter. For decades, these worlds remained largely unchanged in our understanding. But the data from that brief encounter did not remain static. In 2023, researchers returned to magnetometer readings, measurements of magnetic fields collected during that flyby. A magnetometer detects variations in magnetic forces, allowing scientists to infer interactions between charged particles and planetary environments. Within those measurements, they identified a structure that had not been recognized before. Voyager 2 had passed through what is called a plasmoid, a detached bubble of plasma, meaning ionized gas, that had been pinched away from a source and carried outward by Uranus's magnetic field. The source of that material was traced back to Ariel. This implied something active. A plasmoid does not form from a static surface. It requires a supply of particles, released into space, then shaped by magnetic forces. The most consistent explanation is outgassing, the release of material from a body's interior or near surface into space. For Ariel, that suggests internal processes still operating. But this was not the only line of evidence. Around the same period, updated models of tidal heating were developed for the Uranian system. Tidal heating, the process where gravitational forces flex a moon's interior and generate heat, depends strongly on orbital relationships and internal composition. If a moon contains ammonia mixed with water, that mixture lowers the freezing point, allowing liquid layers to persist at lower temperatures. Under these revised models, both Ariel and Miranda could maintain subsurface oceans, not frozen solid, but existing as layers beneath their outer shells. This possibility aligns with Ariel's surface features, which include extensive networks of valleys and troughs. These troughs are fault-bounded, meaning they formed where the crust was pulled apart, indicating that the surface has stretched and shifted in response to internal forces. Not all of the moons show this behavior. Umbriel, for example, remains almost entirely unchanged in appearance, its surface dark, ancient, and heavily cratered, with minimal signs of resurfacing. Yet even there, a single bright ring feature stands out, its origin still unresolved, a contrast that has resisted explanation since it was first observed. So, we are left with a system where activity may still be present, but only revealed through subtle signatures hidden in decades-old data. A new mission has been proposed to return. In 2022, a Uranus orbiter and atmospheric probe were identified as the highest priority flagship mission for the coming decade, intended to revisit these moons with modern instruments capable of resolving what was once beyond reach. Until then, the evidence remains partial, drawn from a fleeting encounter, waiting to be expanded by a second look. If you widen your view far beyond the bright inner systems, you begin to notice faint points moving in paths that feel misaligned, tilted, and scattered, as if they do not quite belong where they are. These are the irregular moons, a vast population of captured objects that orbit at great distances from their planets, often following paths that defy the orderly patterns seen closer in. Around Jupiter alone, at least 92 of these moons have been identified, most discovered only after the year 2000 through wide field surveys that scan large portions of the sky. The majority are extremely small, many less than 3 kilometers across, too distant and dim to resolve as anything more than moving points of light. We do not see their surfaces, but their orbits tell their story. Unlike regular moons, which follow near circular paths aligned with their planet's equator, these objects move on inclined and eccentric trajectories, often looping backward in retrograde motion, meaning they orbit opposite the planet's rotation. Such motion cannot arise from local formation. Instead, it points to capture, a process where a passing object loses enough energy to become gravitationally bound to a planet. This can happen through interactions with other bodies or through the complex gravitational environment present during the early solar system. Once captured, some of these objects did not remain intact. They group into what are called dynamical families, clusters of moons that share similar orbital characteristics, suggesting they originated from a single parent body. That parent, once captured, was later fragmented by a collision, scattering pieces along related paths. Jupiter's Carme group provides a clear example. At least 17 moons share a common retrograde orbit, their paths closely aligned in inclination and distance, indicating they are fragments of one larger object that broke apart long after capture. Saturn shows similar structures. Its Norse group consists of numerous retrograde moons, each tracing a related orbit that points back to one or two original bodies that were disrupted. But these patterns are not only about individual events, they preserve a larger history. The distribution of irregular moons across the giant planets supports the idea of orbital migration, a period early in the solar system when Jupiter and Saturn shifted positions, altering the gravitational landscape. Orbital migration refers to the gradual movement of planets due to interactions with surrounding material, causing them to drift inward or outward over time. During this era, small bodies were scattered across vast distances, some flung outward, others redirected inward, and a fraction captured into distant, unstable orbits. Many of those captured objects remain today, but their futures are uncertain. Gravitational perturbations, meaning small, repeated tugs from planets and neighboring moons, slowly alter their paths. Some will be ejected back into interplanetary space, others may collide with larger moons, and a few will spiral inward and be lost to their host planet. They are temporary residents, and yet, despite their number, they remain largely unobserved, a population that exceeds the familiar moons by several times, existing at the edges of our knowledge, moving through orbits that still carry the imprint of an earlier, more chaotic solar system. We used to draw a narrow ring around a star and call it enough. Within that band, liquid water could remain stable on a surface, neither frozen nor boiled away, and so the idea of habitability became tied to distance from starlight. It was a clean definition, simple to apply, and it excluded almost everything we have been looking at tonight. Under that framework, the outer planets were silent. Any moon orbiting beyond that zone was assumed frozen through and through, its internal heat long lost, its chemistry locked in place. But observations accumulated, slowly at first, then with growing clarity, showing that some of these distant worlds were not frozen interiors at all. They were active beneath the surface. Europa provided the first clear contradiction. Its ocean is not warmed by sunlight, but by tidal heating, a process where gravitational forces flex a body repeatedly, generating heat through internal friction. The energy source is not the sun, but the constant pull of a massive planet. That mechanism changed the boundary. As of 2024, subsurface oceans are confirmed or strongly supported on at least 6 moons: Europa, Ganymede, Callisto, Enceladus, Titan, and Mimas. Each presents a different configuration, some beneath thick ice shells, others interacting with surface processes, but all share the same essential feature. Liquid water exists where it should not. Beyond these, additional candidates have emerged. Ariel and Miranda show signs consistent with internal activity. Triton exhibits geological processes that imply retained heat. Dione and Rhea display subtle magnetic signatures suggestive of conductive layers below. Even Charon, orbiting Pluto, has been proposed as a possible host for a buried ocean in its past. The list continues to expand. When we consider their combined volume, the scale shifts again. The total amount of water contained within these hidden oceans likely exceeds the surface water of all rocky planets combined. It is not a marginal addition to the inventory of water in the solar system. It is the majority. But this forces a change in definition. The concept that followed is called the tidal habitable zone, a region not around a star, but around a planet, where gravitational interactions supply enough energy to maintain liquid water within orbiting moons. This zone does not depend on distance from the Sun. A gas giant positioned far from its star can still host moons with internal oceans, sustained for billions of years by tidal forces alone. The requirement is not sunlight, but a balance of orbital resonance, internal composition, and gravitational stress. So the map of where life might exist expands outward. Systems once dismissed as too cold are reconsidered. Jupiter, like planets orbiting at great distances with complex moon systems, become viable environments for long-term liquid water. The assumption that warmth must come from above gives way to the realization that it can emerge from within. But this raises a quieter question. If habitability is no longer tied to light, then how many such environments might exist, unseen, beneath surfaces that reveal nothing at all? There is a moment in every long mission when the path ahead narrows to a single choice, not about what to discover next, but about how to end what has already been achieved. For Cassini, that moment came after years of accumulation, when its fuel reserves began to approach their final limits. Cassini launched in October 1997, carrying with it the Huygens probe, and began a journey that stretched across 3.5 billion kilometers before reaching Saturn in July 2004. The spacecraft entered orbit and began a sustained period of observation that would last 13 years. During that time, it completed 293 orbits of Saturn. Each orbit brought new encounters. Cassini performed 127 close flybys of Titan, passing through its dense atmosphere and mapping its surface through radar. It conducted 23 targeted flybys of Enceladus, sampling plumes and measuring their composition directly. It visited every major moon in the system, building a layered understanding of each environment. The discoveries accumulated steadily. It revealed the active geysers at Enceladus, confirming a subsurface ocean in direct contact with space. It mapped Titan's methane seas, tracing coastlines and depths, It identified the source of the E-ring as material ejected from Enceladus. It detected new moons embedded within the rings and refined estimates of the ring's age. But as the mission continued, fuel diminished. Without propellant, Cassini would lose the ability to control its orientation and trajectory. Left unmanaged, it would eventually drift, its orbit altered by gravitational interactions until it collided with one of Saturn's moons. That possibility introduced a constraint. Even spacecraft, assembled in cleanrooms, carry microorganisms from Earth. No sterilization process can guarantee complete removal. If Cassini were to impact a world like Enceladus or Titan, it could deposit terrestrial biology into environments where liquid water and complex chemistry exist. That risk was not theoretical, so the mission plan changed. In its final year, Cassini was directed into a series of 22 orbits that passed between Saturn and its innermost rings, a region never previously explored. These orbits, known as the grand finale, allowed direct sampling of ring particles and measurements of Saturn's gravitational field with unprecedented precision. From these passes, scientists determined that the rings are between 10 million and 100 million years old, far younger than the planet itself. But each orbit also lowered the spacecraft's altitude. The trajectory was designed carefully, guiding Cassini toward an inevitable descent into Saturn's atmosphere. On September 15, 2017, the spacecraft entered the upper layers, its instruments still transmitting data as atmospheric pressure increased. There was no recovery. As forces built, the antenna lost its lock and the signal returned to Earth weakened, then stopped entirely. The end was observed in real time, a final transmission that marked the completion of the mission. But the decision behind that ending was not driven by necessity alone. It was an act of planetary protection, the principle that exploration should not compromise the environments it seeks to understand, even at the cost of the mission itself. There is a rule that sits quietly beneath every mission we have followed, one that does not guide trajectories or instrument design, but limits what we are allowed to do once we arrive. It is not about engineering. It is about restraint. Planetary protection is the discipline that governs this boundary. It exists to prevent Earth life from contaminating other worlds and to prevent extraterrestrial material from contaminating Earth under international agreements coordinated by the Committee on Space Research. It is the only part of exploration where ambition is deliberately slowed, because the problem is subtle. If we search for life on another world and find it, we must be certain it originated there. If even a single terrestrial organism arrives first, carried unnoticed on a spacecraft, that certainty disappears, the discovery becomes ambiguous, and the question remains unresolved. So, the precautions are extreme. Spacecraft intended for ocean worlds undergo sterilization procedures that push current technology to its limits. Components are heated to 110 degrees Celsius for extended durations, exposed to ultraviolet radiation, and assembled within clean rooms where particle counts are restricted to fewer than 3,500 per cubic meter. These environments are controlled carefully, but they are not perfect. Some microorganisms persist. Certain species, including members of the Bacillus group, form durable spores that can survive heat, radiation, and prolonged desiccation. These have been detected in cleanroom environments and even on the exterior of orbiting platforms exposed to space. This persistence creates a tension. Enceladus presents the clearest case. Its plumes rise directly from an internal ocean, carrying water, salts, and organic compounds into space. A spacecraft passing through that plume can collect samples without drilling or landing, a rare opportunity for direct analysis. But contact is not one-sided. Particles from the spacecraft can also enter the plume, and from there, potentially fall back to the surface or into the ocean itself. The act of sampling risks introducing exactly what we are trying to avoid. Landing intensifies the challenge. A probe touching the surface of Europa or Enceladus would require a level of sterilization beyond what is currently achievable. Absolute elimination of biological material cannot be guaranteed with existing methods. Some fraction of Earth life would almost certainly remain. The concern does not end there. If material is returned to Earth, it must be contained under Biosafety Level 4 conditions, the highest level used for studying the most hazardous pathogens. These facilities are designed to isolate and control organisms whose behavior is not fully understood. But with extraterrestrial samples, the uncertainty is deeper. We do not know how alien biochemistry would interact with Earth systems. It may be harmless, it may not persist, but there is no empirical basis to predict the outcome with confidence. So the debate continues. Is it acceptable to risk contaminating an ocean that may already be sterile in order to determine whether it is not? Or does the possibility of altering that environment outweigh the value of immediate discovery? There is a period approaching when multiple spacecraft will be moving through different moon systems at the same time, each following its own trajectory, yet all converging on the same question from different angles. For the first time, exploration will not be sequential, but simultaneous. Europa Clipper began that shift when it launched on October 14, 2024, aboard a Falcon Heavy rocket, setting out toward Jupiter on a trajectory that will bring it into orbit around the system in April 2030. Once there, it will conduct 49 close flybys of Europa, some descending to just 25 kilometers above the surface. At that distance, resolution changes. Its radar sounder, an instrument that sends radio waves through ice and measures their reflections, will map the thickness of Europa's shell across the entire globe, identifying regions where the ice is thinnest and the ocean lies closest to the surface. At the same time, its mass spectrometer will analyze particles in the tenuous atmosphere, searching for molecular hydrogen and complex organics similar to those detected elsewhere. But Europa is only one focus. The European Space Agency's JUICE spacecraft, launched in April 2023, will arrive at Jupiter in 2031. It will spend several years conducting detailed studies of Ganymede, Callisto, and Europa before entering orbit around Ganymede in 2034. This will be a first. No spacecraft has ever orbited a moon other than our own. Sustained observation from orbit will allow continuous measurement of magnetic fields, surface composition, and internal structure, building a dataset that cannot be achieved through brief flybys alone. Farther out, another mission follows a different approach. Dragonfly, scheduled to launch in 2028, will arrive at Titan in 2034. It is a rotorcraft, a nuclear-powered vehicle designed to fly through Titan's dense atmosphere, covering distances of up to 8 kilometers per flight. It will not remain in one place. Instead, it will move between sites, sampling organic materials from dune fields and impact regions. One of its primary targets is Selk Crater, where the heat from an ancient impact would have melted ice and organic compounds together, creating a temporary environment where liquid water existed for a limited period. But not all missions will remain in place. Japan's MMX mission will travel to Phobos in the early part of the next decade, land on its surface, and collect a small sample, approximately 10 grams, before returning it to Earth. This will provide direct laboratory analysis of material from a Martian moon for the first time. And beyond these, new concepts continue to develop. A proposed mission to Enceladus would combine orbital observation with a surface landing, allowing instruments to analyze plume material that has settled on the ice, avoiding the need to penetrate the crust directly. Together, these missions form a network, but what they will find is not guaranteed. Each carries instruments designed to detect chemistry, structure, and energy sources, yet none can promise a definitive answer in advance. The next decade will not close the question. It will narrow it. There is a narrowing now, not of distance, but of possibility, where decades of observation, theory, and careful measurement converge toward outcomes that can no longer multiply. As the next missions return their data, the range of answers compresses into two directions, each carrying its own weight. We have reached a point where ambiguity cannot remain indefinitely. When instruments begin to sample Europa's surface environment in detail, when Ganymede's interior is traced through sustained observation, when Titan's chemistry is tested across multiple locations, and when plume material is analyzed with far greater sensitivity than before, the results will begin to align. They will not scatter, but the outcomes divide cleanly. In the first case, biosignatures are detected, evidence that cannot be explained through non-biological processes alone. Biosignatures refer to patterns in chemistry or structure that indicate metabolism, replication, or organization beyond abiotic reactions. If such evidence appears, even in one location, the implication extends beyond that world. It would mean that life has arisen independently at least twice within the same solar system, once on Earth and once within an ocean hidden beneath ice or hydrocarbon layers. Two origins, separate in environment and history, would suggest that life does not depend on a narrow set of conditions. It would suggest accessibility. Given sufficient chemistry, stable environments, and time, the emergence of life would become an expected outcome rather than an exceptional one. In a galaxy containing hundreds of billions of stars, most hosting planetary systems, many including gas giants with moons, the number of potential environments expands rapidly. The probability compounds. Under that interpretation, life would not be rare. It would be widespread, present wherever the necessary ingredients persist long enough to interact. The question would shift from whether life exists elsewhere to how often it develops complexity. But there is another outcome. If these environments are examined in detail, across multiple worlds, using instruments capable of detecting subtle chemical imbalances and structural patterns, and nothing is found, no biosignatures, no anomalies that suggest biological processes, then the interpretation changes. Absence becomes information. It would indicate that liquid water, energy sources, and organic chemistry are not sufficient conditions on their own. There would be an additional requirement, some transition from chemistry to biology that does not occur readily, even over billions of years. This transition remains undefined. It could involve rare environmental combinations, specific catalytic surfaces, or sequences of reactions that do not repeat easily. Whatever the mechanism, its rarity would imply that Earth's history includes an event or pathway that is not common. That possibility narrows expectation. In that case, the universe may contain many environments that resemble the conditions we associate with habitability, yet remain chemically active without ever crossing into biology. Life would still exist, but its distribution would be sparse, separated by large distances and long intervals. So the distinction is not subtle. One outcome suggests a universe where life emerges wherever it can. The other suggests a universe where life requires something more, something uncommon. And for the first time, the difference between those possibilities may be resolved within the span of a single generation. Before any trajectory is plotted or any instrument powered on, there is a quieter layer beneath each mission, something that does not appear in diagrams or specifications, yet determines why the mission exists at all. It is not a measurement. It is a question that has followed us long before we learned how to test it. Every spacecraft sent toward an ocean moon carries tools designed to detect chemistry, ratios of molecules, patterns in isotopes, and structures that suggest organization beyond random processes. But alongside those tools, it carries something less tangible. It carries intent. The question itself did not begin in laboratories. It predates them, stretching back to the earliest observations of the night sky, when the absence of knowledge left only speculation. For most of history, the question remained untestable, shaped by belief systems, stories, and ideas that could not be verified or refuted. It remained open, but the environments we have been tracing have changed that condition. These moons offer locations where the question can be examined directly, not through abstraction, but through physical sampling. Chemistry becomes the language through which an answer might appear. That shift matters. It transforms a question, once defined by interpretation, into one defined by evidence. We are no longer asking in the abstract. We are asking in places where the answer may already exist, encoded in materials that can be measured and compared. But there is another layer to consider. We are searching in oceans that have never seen sunlight, environments where energy flows through chemical gradients rather than radiation from a star. These systems operate under conditions that differ fundamentally from those that shaped life on Earth, yet they may still produce similar outcomes. The comparison is indirect. At the same time, our own presence in this process is not inevitable. The sequence of events that led to a species capable of building instruments, launching missions, and interpreting results depends on a chain of contingencies that cannot be repeated easily. We are part of the experiment. If life exists in one of these oceans, it has developed in isolation, without any awareness of external conditions beyond its environment. It would not observe stars or planets or the structures we associate with a wider universe. Its context would be local, bounded by water, chemistry, and internal energy sources. Its timeline would be long. Such life, if present, may have persisted for hundreds of millions of years, potentially longer than complex multicellular life has existed on Earth. It would have its own processes, its own stability, its own constraints, all unfolding without interaction with anything beyond its ocean. But when we detect it, if we do, the change will not be mutual. The discovery would alter our understanding immediately, reshaping how we interpret life, its distribution, and its requirements. For the organisms themselves, nothing would change. The detection would occur at a distance, through instruments and data, without direct interaction. So the question we carry is not only about existence, it is also about perspective, about how a single confirmation, drawn from a hidden ocean, would shift the way we see everything that surrounds us. If we step back from individual worlds and hold them together in a single frame, the solar system begins to feel less like a collection of objects and more like a layered record of time itself. Each moon preserves a different tempo, a different way that change unfolds. Some surfaces remember everything. Callisto carries an uninterrupted history stretching back roughly 4 billion years, each impact fixed in place, each crater overlapping another in a sequence that has never been erased. When you look there, you are not seeing a moment. You are seeing accumulation. Other worlds refuse memory entirely. Io exists in a state of constant renewal, its surface reshaped faster than impacts can be preserved, its history continuously overwritten by molten material rising from below. Nothing lasts long enough to become a record. It is all present. Between these extremes, other moons operate on slower, quieter cycles that stretch beyond immediate observation. Titan has been conducting a chemical process since Saturn formed, its atmosphere and surface exchanging material over spans measured in billions of years. Organic compounds settle, accumulate, and transform without interruption. The experiment continues. Even futures are already defined by these same long patterns. Triton, moving in its retrograde path, is gradually losing orbital energy, a process so slow it feels static, yet precise enough to predict its eventual destruction. In approximately 3.6 billion years, tidal forces will overcome its structure. It will become debris. Those fragments will not remain fixed. They will spread, thin, and disperse, forming a transient ring before scattering further, gradually blending into the broader structure of the solar system and eventually beyond it. Nothing stays confined. But the largest change will not come from the moons themselves. It will come from the star they orbit. In roughly 5 billion years, the Sun will enter its red giant phase, expanding outward and increasing its luminosity, altering every environment in the outer system. Ice will not remain stable. The outer layers of Europa and Enceladus will absorb that energy, their frozen shells warming, softening, and eventually melting from above. Oceans that have been sealed for billions of years will be exposed, their contents no longer protected from vacuum. Exposure will be brief. Water will escape. Molecules will break apart under radiation, and any complex chemistry or biology that depended on isolation will lose the conditions that sustained it. The transition will not preserve structure. It will reduce it. What remains will be residue. After the red giant phase, when the Sun sheds its outer layers and contracts into a white dwarf, temperatures will fall again, and the outer solar system will refreeze. But what returns will not be what existed before. It will be simpler. These timelines stretch across billions of years, each process unfolding at a pace that resists direct experience. We observe fragments, short intervals within much longer sequences, and we build understanding from those limited windows. Our view is narrow. We have been studying these systems with precision for less than 100 years, a fraction so small it barely registers against the age of the system itself. And yet, within that brief span, we have already seen enough to know that time here does not move in a single way. It unfolds differently everywhere you look. Long before any spacecraft crossed the outer planets, we believed we understood what mattered. We thought the story would be written in the planets themselves, in their atmospheres, their rings, their visible surfaces. The smaller companions were expected to be incidental, fragments left over from formation, interesting perhaps, but secondary. That assumption did not survive contact with data. As observations accumulated across decades, patterns began to emerge that did not fit the original framework. Beneath surfaces that appeared frozen and inert, processes were continuing, driven not by sunlight, but by gravity, chemistry, and time, acting together in ways that were not immediately visible. The interiors held everything. The count of known moons has grown to more than 290, each one offering a variation on the same underlying theme. Conditions that appear hostile at the surface often conceal environments that are stable, persistent, and energetically active below. This changes the map. Habitability is no longer defined only by distance from a star or by surface temperature. It becomes a question of internal structure, of whether energy can be generated and retained, of whether liquid environments can exist in isolation for spans measured in billions of years. The criteria simplify. Chemistry provides the building blocks. Energy drives reactions. Time allows complexity to accumulate. These are not rare conditions. They are widely distributed, repeated across multiple systems, expressed in different forms, but governed by the same underlying principles. But distribution is not confirmation. We have not yet observed a second instance of life beyond Earth. What we have observed are environments that meet the known requirements, systems that mirror the conditions under which life here emerged, yet remain untested in the one way that matters. The answer is still absent. There is a particular stillness associated with these worlds, not because nothing is happening, but because what is happening unfolds beneath layers that conceal it from direct view. Europa moves through cycles of light and shadow, its internal ocean responding to gravitational forces it cannot perceive. Enceladus releases material into space, a continuous exchange between interior and exterior. Activity without visibility. From our position, confined to a single planetary surface, the scale of this system is difficult to internalize. We have explored only a fraction of these bodies, often briefly, sometimes only once, gathering limited data from encounters that lasted hours within environments shaped over billions of years. Our sampling is thin, but the question that has followed us through earlier sections does not change in complexity, only in context. It is no longer abstract. It is tied to specific locations, specific missions, specific measurements that can be made within a defined time frame. It is within reach. What remains uncertain is not the presence of suitable environments, but whether we can approach them without altering them, whether our methods can preserve the distinction between what originates there and what might be introduced unintentionally. Care becomes part of discovery. These oceans have existed for spans far longer than complex life has existed on Earth, maintaining conditions that do not depend on external warmth or light, evolving according to internal dynamics that proceed regardless of observation. They are not waiting for us, and yet, for the first time, you and I are part of a moment where the distance between question and answer is no longer measured in imagination, but in missions already underway, in instruments already built, in data that will arrive within a single human lifetime.